Okay, let's get started. So, welcome to another lecture as part of our ID 5130 Parallel Scientific Computing course. All right. So, in today's in today's lecture, we're going to kind of look at the motivation and kind of motivation for using a reduction clause. Okay, so this is and then we will try to introduce this, and depending on the time we are also going to look at the parallel for directive, okay, in OpenMP. All right, so if you recall, in the last lecture we ended up basically looking at the trapezoidal rule, right, to calculate integration of a certain function using the trapezoidal rule, right? And then we also kind of wrote or looked at both the serial as well as the OpenMP versions of the program, right? Where we kind of made use of a separate function to calculate the partition or the part of each threads, right? And then we kind of ended up adding all of them using a critical section, right? So that's what we looked at in the last lecture. So we will start off with that by looking at the program and then try to kind of provide some motivation and then look at what is the reduction clause in today's lecture. All right, let us open the program. So this was Emacs program OMP parallel trapezoidal. Okay, so what we did was basically we have, of course, all of these things. We have this was the original function, and then this is the trapezoidal rule program right up till here, and then the main program we had some values here, N, A, B, and then we had this trapezoidal rule call, right? Now we may see that, okay, let me first copy this program to something else. Copy program OMP parallel to program OMP trapezoidal v1.c. Okay, so let us open this program. This is program OMP trapezoidal v1. Okay, so this is the same code. Now let us say we don't want to, or we don't like the pointers way here of the star result, and we want to kind of write this program in a different way. Okay, so the different way we're talking about is, instead of sending the value, right, of the final result by sending its address or by kind of modifying this thing, we would like to write this as a return variable. Okay, so instead of having this function that is basically your so as of now we have your trapezoidal rule function has no return, so that is void, but then here it kind of takes integer, right? It takes an int n, it takes a double a, and then it takes another double, and then it also takes address of double, right? So that's what it is. So that's what we have, but then we don't want to have this passed as an argument, rather we would like to have it as a return type. Okay, so this function when called would return the total integration value for that particular thread, okay, instead of this. So that means we would like to write the program like this. So essentially you pass double a, double b, that's all. Okay, so we'd like to write something like this and see if we can still continue with our parallelization. Okay, so essentially we may encounter something like this when you write your own code. So let us try to convert this program so that instead of having the final result passed as an argument, we would like to have it as the return type. Okay, so let me change this thing. So let's start with the function itself. So here we would write, instead of void, we would write the double. Okay, so it's going to return this, and then we don't need this final as an argument. Okay, then because we are not doing the same, I'm going to also remove the hash pragma critical. I'm going to return the star result because we are not passing it anymore. So I'm going to return total here. Okay, so this is return total. Okay, let's that will be returned by this function. Okay, so essentially now our function is modified such that it returns the total value it computes, right? This basically would be the total for each thread, right? This is basically a private variable, right? Okay, because so this will be local and private. We have already written it here in yesterday's lecture. Okay, now this is fine. Now what about, but we have to also remember that we removed the hash pragma OpenMP critical, so that needs to be kind of come in somewhere. Okay, so we need to keep in mind that. And then so essentially we have final is equal to 0, and then we are forking a parallel section here in hash pragma OMP parallel num threads thread count, and then we say trapezoidal rule. Now of course we are not passing anything here, so ampersand final result is gone, so we just have this, but then we need to somehow get this thing. So final result plus equal to, okay, this is basically saying as same as final result plus, right? So this is just a shortcut. That's basically plus equal to would be the shortcut for the expanded form. Okay, so final result plus equal to trapezoidal rule, and pass the number of trapeziums and then a and b, the left and right values, okay, of the integration. Fine, now we got something, but this is not correct, isn't it? Because now why is this not correct? Because if you leave it like this, essentially it's going to create a race condition, right? And then the result will be uncertain, right? Or undetermined, right? So it's kind of non-deterministic. So as a result, now we have to essentially add that hash pragma OpenMP parallel, hash pragma OMP critical somewhere, right? So we would do that. So whatever we have removed from the function, we would do that. So let us try to put the hash pragma OMP critical in here. So for that, I would like to kind of make this as, so we have already final assembly set to 0. Then we would say, okay, now this is basically your code. Okay, so this is the structured block, and here we would like to write hash pragma OMP critical. Okay, so that's now the critical section, and then we just basically have the same code that we have written before, but in a slightly different way. Instead of having it as an argument, we have it as a return type, right? Okay, now this should be working the same way it should be. So let us try to compile this. So this is gcc minus f openmp program omp trapezoidal v1 minus link math. That should do. Okay, now we got the a.out, so I say /a.out because we have given 100 as the type here. I would like to run with maybe 5 cores. Okay, so we got 5.14128. This seems to be the same value we got before yesterday as well. So the code seems to be working fine, but there is something not. There is some issue with the code, right? Can you see the problem with this particular code? So this code is perfectly fine, but there is a big trouble, a big big drawback with this code. What is the big drawback with this code? The drawback is that because we have set the OpenMP, or the shortcoming is that because we have set the hash program OpenMP critical, and then we have written this final result plus equal to trapezoidal rule, we are forcing this entire function called trapezoidal rule to be called by each and every thread, okay, one after the other, right? That means we are forcing a call to the trapezoidal rule in a mutually exclusive way for the thread. That means every thread will not only execute this summation in a sequential way, but it also executes this call to the function in a sequential way. So as a result, although the final answer you get would be the same, the time it takes for this would be, in fact, will be more than what it would take for a serial code to compute, because now you have the additional task of creating the threads and then calling these threads one by one and so on. Okay, so as a result, this is in a performance, if you calculate the runtime for this particular code, this will come out to be larger than the corresponding serial code for the same number of n and n. Okay, so if you consider 100 points, it will probably come out to be larger. So as a result, this is not a good program, because now we are kind of serializing the function call itself. Okay, so what we can do is, well, okay, then what we would do is we would resort to the previous trick. That means instead of calling this function also into the critical, we can have another local variable, right? So we can say, okay, I will now basically define another local variable, which I would like to call it as, let's say, double my result equals 0.0. Okay, I define a local variable, and then now because this is now created inside this hash pragma OpenMP parallel, this is basically local and it is private for each thread. So every thread will have its own copy of this thing, and then I don't need this critical here, so I would just cut this and then save it for later, okay, which we would use maybe. Okay, then what I would do is, okay, fine, so instead of final result equal to plus, I would say my result. So that means this would be my result. Okay, my result equals we have this value, right, equal to trapezoidal rule. Okay, and then my result, we can say it's coming out to be in parallel, so this can be my result equal to local trapezoidal rule. Okay, now what we would do is each of them will return the corresponding result, and then we can have the critical section, right? So the critical section now will add basically final result equals or plus equals my result. Okay, so that would now should also work correctly, and it should also not have that performance penalty that we had before, where all the threads were calling the function trapezoidal rule in a sequential way, right? So now that is now alleviated. That's not there. So basically the trapezoidal rule will be called in parallel, and then once all of them will calculate their own result values, they are going to basically wait in the hash program OpenMP critical and then add all these my results into final result one after the other. Okay, so let us see if this program compiles and gives the correct answer. So this is basically OMP same one. Okay, so it compiles, and then I say /a.5. Okay, it has given the same answer as before, so that is fine. Let us try to run it maybe with something else. 10. Okay, it's giving the same answer. I would say this is 100, so I can see 2. Okay, so it seems to be working fine. So 4 also should be fine. Okay, so then, okay, so this is good. So this is basically nothing but same as what we had before, right? Only thing is that the code now is basically returning the calculated value, then it is taking it as an argument. Okay, so that is what it is. Now whatever we have done is basically we basically have a critical section, and then we also have declared a private variable. Okay, so that's what we have done. So in the process of doing all this, what we have done, if you notice, so what we have done is basically created a private variable or a local variable, right, which is for each thread, where each thread can store its copy, and then essentially move the hash pragma OMP critical after the function call. Okay, so that this can be basically is only doing the, so the critical section is only for the addition, right? Okay, it's not doing it for the function call. As a result, this will be somewhat this will be definitely faster. Okay, that's what we are. Now the same thing whatever we have done, OpenMP provides a, so this kind of serves as the motivation. So OpenMP provides a cleaner alternative okay, for this. That means we don't have to necessarily create a local variable ourselves and then think of initializing it and then moving the OpenMP critical section to after the function call and so on. We can use something known as a reduction clause. Okay, that's what OpenMP provides. So OpenMP provides something known as a reduction clause, okay, or a reduction clause, and this we can use this to essentially perform whatever we have done in a much cleaner and simpler way. Okay, So what is a reduction clause? A reduction clause is something that works with a reduction operator. Okay, reduction operator, and reduction clause also would have something known as a reduction variable. Okay, you would know what is a reduction. Reduction is basically performing the same operation over and over again on a set of elements. Okay, and storing the temporary value each time in the same variable. Okay, what is this same variable? This is nothing but the reduction variable. Okay, that means if you might have kind of come across some code that looks like this, right? You may have int let's say some float. Okay, let's say double total equals 0.0. You might have come across a code like this, where for I equals 0, I less than n, I plus plus, right? You might have come across something known as total plus equals some array. Okay, so we have basically an array of I. So what does this do? This basically will add elements of array A one by one to total, and while it is doing so, it will basically store that progressing value of the addition in the total. So in this, plus serves as the reduction, operator. Okay, this is the reduction operator, and total is your reduction variable. Okay, so that's what we have now. Essentially in OpenMP, it is possible to specify that the result of a reduction variable or reduction operator is a reduction variable. Okay, so essentially what we do is, in order to do this, we would use the reduction clause, and the reduction clause will go together with the hash pragma OpenMP. Okay, that means what we need to do is, in our code right now, what we have is we need to write final result plus equals some function call with something, right? Now our final result is the reduction variable, and this plus here would be our reduction operator. Okay, so that's what we have to do. So how do we write this? Essentially, you would write hash pragma OMP parallel, okay, num threads, and this is some number. I'm not writing this because everything else is basically will go are basically the directives, right, for OpenMP. So but num threads, this one thread count is some number. Okay, let's say 8 or something. I'm just putting a number in here to say that this could be a variable. Okay, this is not variable name, this is not a directive. Okay, so this can be anything, right? Okay, num threads, and then we would continue. If you want to continue, you can write it here, or you can have a continuation symbol for this one, and then you say your reduction is the clause. Okay, so this is the clause, this is the reduction clause, this is the keyword. Okay, so this is the OpenMP clause, and then what you have is in the reduction we want to perform summation. Okay, and then you have you want to perform it on final result. Okay, so that's what you have to do, and then of course this should follow a structured code block. Okay, that should follow this one. All right, so how do we do this? So essentially we'll go back to the program, and then we would change this. So this is your okay, so we don't have to now essentially have this. So basically reduction plus colon, and then we have final result is what we do. Okay, so and then I can remove the my result. I don't need the private variable because this will be automatically done by OpenMP for us. So that is the high level programming, you know, the benefit of high level programming, right? So final result, and then you would say final result plus equal to OpenMP trapezoidal rule NAB. Okay, so this is basically, now we don't need to have the hash pragma OMP critical. I can remove this. I don't need this one. So essentially we have removed pretty much everything. I can also remove this curly braces, not required anymore. Okay, so this is so simple. Okay, it's very nice. We just have again couple of lines here. So hash pragma OMP parallel num threads thread count, and we are specifying that final result is a reduction variable. Okay, and what needs to be done is, and the plus is a reduction operator. So only these two would be executed in as a critical section in a mutually exclusive thread exclusive way. Okay, whereas the call to the trapezoidal rule will be, okay, call to trapezoidal rule will be parallel. Okay, only the reduction clause specifies that plus needs to be protected as a critical section. Okay, so this should basically run, hopefully, when you try to run it now, and give the same result as we got before. Okay, now it says some error. Final result plus equal to, oh, I have a space there, is it? Okay, plus equal to should be together. Okay, all right, okay, fine. So it basically compiles, and then now I can run it, /a.out 5, we get the same answer, 5.141428. Run it with maybe 10, 2. Okay, so this is running fine. All right, so what OpenMP has essentially done is it has created a temporary, or it has created a private variable called final result for each thread. Okay, so let us write it down. Okay, so we have now written it to be as so what OpenMP has done for us, you know, behind the scenes, is basically when you wrote this particular final result reduction equal to final result, what it has done is it has created a private variable, okay, for final result for each thread that we cannot see here. Okay, so it created a private variable, okay, and it has used that final result private variable when each thread is executing. Okay, when each thread is executing the code, it has used the final result, the private variable final result. That could be maybe, you know, let's say for example, if you somehow have access to the how OpenMP is doing, it could be final result, let's say T1, okay, and then T2 for each of the threads, something like this, T3 and so on. So when each thread call is happening, that is when each of them is calling trapezoidal rule, okay, it is executing all this in parallel, unlike the previous code where it was executing in serial. Okay, now it is executing this in each of them in parallel, and then when they are returning, they are not actually returning to the final result, which is actually a shared variable, right? Because final result is declared before the hash pragma, right? So as a result, final result is a shared variable, but what OpenMP has done because of the reduction clause is that it has created a private variable for each thread, and it has used that when returning it, and it has also created a hash pragma OMP critical, okay, another code in which it has added all these guys, final result T1, T2, T3 into final result, okay, one by one. So that's what OpenMP has done internally. So that means this code is the same as the code that I have unfortunately deleted. Okay, so it will be the same as the previous code that we have deleted. Okay, let me write that one again here. So that is basically hash pragma OMP parallel num threads, okay, thread count. This is what we had before, right? We had this, and then we had double my result equal to 0.0, right? We have hash double my result equal to 0, and then my result equals trapezoidal rule NAP, okay, and then we have hash pragma OMP critical, okay, in which we have added final result was equal to my result. Okay, essentially this code is now, okay, this block of the code is the same as what we have done below. Okay, so OpenMP is essentially doing a similar thing behind the scenes, and when we say that we have used the reduction class. Okay, so that is the kind of motivation and why we should use the reduction class, because it kind of saves time, and and the call to the trapezoidal rule is not serial anymore. Of course, it is not serial either in this one as well. Okay, in this also it is a parallel call here as well. Okay, all right. So that is the motivation. And coming to the reduction syntax for reduction. Okay, only one of these to be executed. So I would just comment this one for the sake of clarity. Okay, and we don't do it 2 times. Okay, then when coming for the syntax for the reduction class, so the syntax is you have to say reduction, okay, and it has to be within the hash pragma OMP parallel on threads, this one, and then you have basically the operator colon, you have the variable list. Okay, that means the operator can be either plus, minus, multiplication, division, multiplication, or it can be even your bitwise operators as well. Okay, and then here you would specify all the variables on which this reduction operator will work on. Okay, now the thing is, that means yeah, so and this is kind of very similar to the Fortran. We will probably come to the Fortran maybe in the next lecture or something, just to quickly go through how this works in Fortran, but we can do it in that as well. Okay, now this is how kind of the reduction operator will work. Now what about the default values? See, for example, what we have done is, in the context of here we have set final result equal to 0, right? And then so here we have said that my result equal to 0, right? And then with my result equal to 0, you could kind of add it to this values, right? Whereas now what would be the value would be taken by final result is basically it will be initialized to 0. Okay, so what OpenMP does is, OpenMP for the private variables it is creating, so OpenMP will initialize the private the threads private variables. Okay, so that is basically when you say final result, it is creating its own threads variables, right, behind the scenes. Now those it will initialize it to 0. Okay, now it will initialize to 0 because the general rule is basically that the private variable will be initialized to the value of the, or to the identity value of the operator. Okay, so the identity value for operator plus or minus is basically 0, and the identity value for multiplication or division is 1. Okay, so the private variables will be initialized to these values. Okay, so that is the general rule in initializing the private variables. So that should be fine. Okay, so that is the motivation for using a reduction clause in OpenMP programs. Okay, all right, so let us now go back and let us now introduce the parallel for directive. Okay, and see if we can rewrite our code for trapezoidal rule using parallel for directive. Okay, so the next thing we would like to discuss today is the parallel for directive. Okay, so where parallel for is this is the keyword. Fine, so that is the OpenMP keyword. All right, so let us open our serial program. Emacs program serial trapezoidal rule. Okay, so we have the serial program. Let us close this guy. Okay, so we got the serial program, in which what we have done is we basically have the function and we have the trapezoidal rule that is computing all these things, and the main code is kind of calling them. Okay, so now if you have to let's say parallelize this in a different way. Okay, so what we are trying to see is an alternative way of parallelizing this thing. Okay, so initially what we said is we have these we have used different the different threads were kind of having different sections of the trapeziums, and then they were adding them and then bringing it together. Now if we have already a for loop, OpenMP kind of provides a convenient way to parallelize this for. Okay, so if we were to start with a serial program and then you just have to make this OpenMP parallel, it can be done very easily without the need for all the two codes, or the code that we have seen yesterday and today, in a very easy way. Okay, so let me slightly rewrite this code so it will be easy. You have a plus I star h, and I will just get rid of this x, so we just have one total. Okay, fine. So we have basically for total plus equals function a plus I star h. So basically it's just adding all of these things. So this is the serial code. Of course it would not run in OpenMP right now, but what I want to do is I want to if I want to make it parallel, I can simply say that I can use the parallel for directive, that is basically hash pragma OMP parallel for, okay, that is basically the for loop num threads thread count. Okay, so what I have done is basically we are now declaring a parallel for instead of just parallel. Okay, so remember parallel was what was parallel doing? So hash pragma OMP parallel was requiring a structured block of code. Okay, whereas hash pragma OMP parallel for requires of course a for loop. Okay, a for loop must follow this hash pragma OMP parallel for directive. Okay, now of course Fortran doesn't have for loops. Fortran has something known as do loops, right? So we will see later how to do it, or even you can figure it out how to do it. It's basically just a similar commands there. Okay, so parallel OpenMP for should follow a for loop below that. Alright, so now we have done the parallel for loop, num threads, and then for I equals 1 to I less than equal to n minus 1 I plus plus. Okay, now this looks fine. Only thing is that now the moment you write parallel for, this I, whatever you have, would be, unlike the parallel, this parallel for would make I to be a would it make a shared variable or a private variable? I, or what do you think should be the correct one? If it is shared, it doesn't serve any purpose, right? If it is shared, that means everybody will keep updating I values, and then there is no way it can kind of work with. So this will be made a private variable. Okay, so I will be private for each thread. Okay, so this will be private. That means the work that needs to be shared, that is this loop, will be shared by the threads. Okay, so this is what differentiates parallel for from parallel directive, because in parallel for, let's say if you have n equals maybe 100 or something, or let's say n minus 1 equal to 100 or something, then that 100 will be pretty much evenly divisible, or you divided between the number of threads. That means if you have 100 by number of threads will be given for each thread. Okay, that means when you use a parallel for, let's say if the iteration has some number of iterations is n iterations in the for loop, then n by number of threads will be assigned for each thread. Okay, so each thread would compute only this part, and as we have noted, I is a private variable. Okay, so this is very important. Unlike hash, pragma, OMP parallel, in which when we wrote the variables that we have used, right, all the things that are coming here, let's say for example n, a, b, these were all declared before, and these were actually shared variables, right? You remember, these were shared variables, and whatever was declared here would only be the local or private to the thread. Okay, whereas here I is a private variable. Well, it ought to be, otherwise it doesn't serve any purpose, right? Because everybody will write to the same location, and it is not correct. So I will be a private variable. As a result, n by number of threads will be assigned to each I. Each thread will be looping over so many points. Now, is this correct? It doesn't seem to be correct, isn't it? What is that we are probably missing here? You know, we wrote hash reduction, hash pragma OMP parallel for num threads. Yeah, reduction is something that we are missing, isn't it? We have to have a reduction for this one. Otherwise, again, there will be a race condition. So what we need to write is, we need to say here, and we can either write it here or write in a different line. I would just write it here. We say a reduction operator is plus, and then colon, and what would be the variable that is taking reduction? So that is total, right? Reduction plus colon total. Okay, so that will be now makes the code correct. Okay, so total plus equals function a plus I star h, total equals total times h, and then we don't need this star result, isn't it? Oh, we need it because we are returning. Okay, so we need that. That's all. Okay, and then this will print. So we have pretty much converted our code into a parallel trapezoidal rule without going through the pain of creating, you know, all the local A, local N, local B, but that is required to understand how OpenMP actually works. So you may have to do that sometimes. Okay, so but if you have a for loop, you can easily parallelize it with this by identifying what are the which operators or which reduction variables should be there, and otherwise if there is a divisibility of work, we can do this. Okay, so now we can see that the parallel directive is very different from parallel for, because in a parallel directive, what we had that the structured block of code was executed by all the threads, whereas in parallel for, the for loop or the work that is required to be done needs to be shared by the threads by themselves. Okay, so they have to share the work, and they have to divide that work by themselves when they kind of come here. Okay, so that makes parallel for to be very different from parallel directives, and we have to also keep track that I is now a private variable, not a shared variable. All right, so that is what it is. And then now if you have to make this, let's say if you have a program, or you know, your research problem or something, and then you have several for loops, then all you have to basically do is basically have this incrementally or parallelize each and every for loop in the same fashion. Okay, so if you do that, then your core code, let's say it's progressing like this, and then you end up with a for loop, and you would kind of parallelize it to work with separate threads, and they will work together, and then when the parallel for loop finishes, they will come back, and then you have some section which is again serial. Then when you encounter another for loop, you would basically fork out into number of threads, and then you would do this, and then the entire program would be kind of like this, isn't it? If there are, let's say, several for loops, that needs to be parallelized. Okay, now if you are lucky, and if you have only one big for loop for the entire code, then all you have to do is just place one command, this hash pragma OMP parallel, and you are done parallelizing the code. That's all, right? That's all. Okay, of course we are not so lucky, so there will be a lot more problems in our codes that we work with. All right, so now of course this is if I were again, if not private, then again we see that there is a problem with this, right? This will be basically a unprotected, if I were not private and if the reduction operator is not given here, this will be an unprotected critical section. Okay, so that we need to keep in mind. Okay. All right. Now, of course, this will not work because I don't have the corresponding hash include. What do we require? OMP.h. That's not included before in the serial code. Okay, I'm modifying the serial code, which is probably not a good idea. Okay, I'll revert it back. And then we also need num threads. So the thread count is not defined, right? So thread count needs to be also defined. So we need to add that variable here as well. So once you do all those things and try to run this should run as well. Okay, this should run and give you the correct answer as well. Okay, so that is the essentially the what we wanted to cover today. You can do similar things with the Fortran codes as well, which we will maybe look it up later. All right. Okay, so if you make all these changes, it will basically give you the same answer as we got before with the previous program. Okay, all right. So I'm going to stop here for now, and then we'll continue in the next lecture. All right, thank you.